Welcome to the TechX Chemistream webinar. We'd like to thank everyone who's attending this webinar and hope you find it interesting and informative. This is the outline for the webinar today. Background for the project lead and the Chemistream project, followed by demos of just some of Chemistream's capabilities, with questions and answers at the end. The project lead, Dr. Scott W. Sides, has experience with a wide range of simulations to address materials modeling, including molecular dynamics at Sandia National Laboratories, self-consistent field theory modeling of block copolymer mixtures. Dr. Sides has been with TechX since 2005 as a designer-developer for the TechX EMPIC code Vorpal, the SCFT code PolySwift++, and Chemistream. So what is Chemistream? Chemistream provides a streamlined and user-friendly framework for managing complex HPC material simulation workflows on various hardware platforms, including HPC cloud resources at AWS, an internal HPC cluster, or your local desktop. Chemistream provides three primary capabilities: turnkey HPC cloud access, pre-configured open source proven simulation codes, and customized GUI workflows that address specific industrial and commercial modeling needs. Chemistream has a large number of simulation codes focused on advanced materials development and is continuously adding new capabilities. Here we show a list of currently available codes for molecular dynamics, quantum chemistry, and more coarse-grained methods such as Kinetic Monte Carlo. Other packages include materials AI models, visualization, simulation setup, and analysis tools. Now let's go on to pre-recorded demonstrations of Chemistream that illustrate some of its capabilities. The first demo will show how a user can easily set up a multi-node cluster at AWS, while others are examples of specific workflows running a variety of material simulations and modeling engines. So first, let's see how to set up a multi-node cluster at AWS. This is the main Chemistream window. From here, we can see the main documentation, which includes general information about Chemistream, info on setup and installation, and other tutorials. From this main page is where we can start a remote compute session. Here we can see a list of compute images available. Let's pick NWChem here as an example. Here are parameters needed to set up the cluster. This is a session title that refers to a collection of instances in the cluster. Here we can set the number of instances in the cluster. And here are the instance types available from AWS. Below there is shown the capabilities of this particular cluster. Now let's launch it. In the window below, we can see some of the setup steps involved in configuring this remote cluster. We can see that the check for internet speed is done, and the instances are now starting at AWS. And in the interest of time, we will skip ahead 3 or 4 minutes. Here you can see the remaining startup steps, including downloading the compute images of interest, starting up a Slurm scheduler, and starting up the Jupyter Lab server, which will serve as the main user interface. Now let's connect to the session. This starts up a tab at the top of the main window and starts up the main Jupyter Lab interface to the compute session. The first page is an interface to remote storage at S3, where you can upload and download files from S3 directly inside the compute session running at AWS. Now let's go to the file browser, showing files and directories inside the NFS shared directory, which is part of the Chemistream framework setup for a cluster. Let's go to this examples directory, which contains files and directories needed to run particular workflows. Here are some subdirectories containing different workflows. Inside this particular one are Python modules and Jupyter Lab notebooks that perform distinct workflows. Now let's walk through a particular Chemistream workflow. The first workflow runs the NWChem quantum chemistry code to calculate the HOMO-LUMO levels of a user-specified molecule. Here is the main Chemistream window again, where 3 clusters are currently running. One running NWChem, one running LAMMPS, and another running a custom ALD simulation using SPPARKS. There are a number of things shown, including the instance types on which each of these clusters is running. Now let's go to that tab. Here we see the startup window again. We'll go into the example for NWChem. Go to the standard example. And here we see a number of notebooks representing different workflows. The main difference between these is in the input methods. These two allow inputting molecules with a set of smile strings. This one allows one to draw a molecule and do a scaling study. Here we see a menu that allows selected inputs to generate NWChem input files. There are a number of different settings controlling the relaxation of a molecule. One can specify solvents, different basis sets, and different functionals. Again, these are restricted to certain choices within NWChem. Here we can pick to do 4 runs, and we can choose the number of processors for each run. Note that for 16 nodes, this is across 2 separate instances. There are a number of different methods for input. There's a drawer, as well as the other 2 that allow input of mole strings. So let's draw a molecule. Start off with pentacene, and then hang a nitrogen off one end. The Chemistream tools are included to allow pre-optimization of the molecule using molecular force fields. One can choose the number of embeds to use. And here you see that a molecule has been embedded and an initial relaxation performed using RDKit. Note that these simulation directories have been created for each different number of processors. And here we submit all of these jobs to a Slurm scheduler that is running inside these containers. Now we can check the output logs and the state of the Slurm scheduler. This shows the last lines of the output for each log and shows the running jobs. In the interest of time, we will skip ahead to when the jobs are done. Here we are, the jobs are done. You can see there are no more jobs in the queue, and this is the end log message from NWChem. Now let's go down to the section where we're parsing the output. Here are some of the timing values. And these are plots of the HOMO-LUMO levels. This is versus iteration for the relaxation steps. You can see first we have an included step where there's a relaxation at a lower basis, and then we turn on the chosen basis set. Now let's generate the scaling plot. This parses out the times and plots them versus number of processors, and we see good scaling results here, especially across the boundary of going from 1 to 2 nodes. This node had about up to 5 gigabits of network performance, but others can be chosen for higher performance. We also provide parsing out the orbitals, and in this plot you can choose looking at the HOMO-LUMO levels for this workflow. Here the HOMO levels are shown on the left, and the LUMO levels are shown on the right for the molecule that we've drawn. The results have been stored in this JSON file, and if you right-click on the file, Jupyter Lab allows a download from the cluster directly to your local machine. The third demo shows how to use a trained artificial intelligence machine learning model called ALFABET to predict bond dissociation energies. This model was developed by researchers at NREL who used a database of over 42,000 closed-shell compounds with 9 or fewer heavy atoms and consisting only of carbon, hydrogen, oxygen, and nitrogen atoms. DFT enthalpy calculations were then performed on these molecules to yield over 290,000 unique bond dissociation energies, representing over 80 days of total CPU time. Here we see a session using ALFABET has already been started, so let's connect. And again, we start with the remote storage interface page. Let's go to the example containing the ALFABET workflow and start that workflow here. We've included a link to a paper from the researchers at NREL who developed ALFABET for your convenience in looking over the details of the model. Now let's start up a drawer so we can specify the molecule for which we want to calculate the bond dissociation energies. Again, remember this model has been developed for molecules containing only hydrogen, carbon, oxygen, and nitrogen. So just as an example, we'll draw a molecule containing all of those. Now we're ready to load the ALFABET model. After it's loaded, the model runs its predictions for each of the allowed bond dissociation breaking events. Now it's done. And the last part of the menu lets a user see the results from the calculations. This table shows a number of things: the SMILE string for the initial molecule, the bond type, and the SMILE strings for each of the 2 fragments, along with the bond dissociation energy for that bond. This part of the menu lets a user scroll through diagrams corresponding to each one of these fragments. The fourth demo is an example of using the Kinetic Monte Carlo code SPPARKS from Sandia National Labs to model atomic layer deposition. The specific atomic layer deposition model has been developed by TechX and NREL as an example for one of our commercial beta testers, Forge Nano, who manufactures advanced coatings for a variety of applications. So here we are back at the main Chemistream window. We've already started a SPPARKS ALD model. Let's start that up. Go to the examples directory and start the workflow. Here are some parameters exposed to the model and a link to the SPPARKS documentation for convenience. So let's first select a unique job tag to distinguish it from other runs. And there are 3 substrate structures to choose from. Let's choose the structured pattern. And here are some other parameters in the model that are described in a report that we will see soon. And let's at least set the size for this example. We'll set the number of cycles for the deposition process, and then initialize the system and bring up an illustration of the substrate structure. So again, this is the structured substrate. This is one particular hard-wired configuration, this array of pillars on a flat substrate. There's a detailed description of the report included for convenience. With Kinetic Monte Carlo, one defines rates of events. And here we have absorption, desorption of species, diffusion of species along the surface, and each species can react on the surface. Now for the run we'll show, we will pick one of these 5 conditions shown here, where a range of deposition pressures for each species, deposit times for each species are defined. And here we have some runs that were performed previously, going from good deposition conditions to slowly worsening deposition conditions. In the run, we'll choose this third condition, which is an intermediate quality of deposition. So here we're back to the workflow. Let's pick a parallel job. We'll choose 8 cores and run the simulation. Here is the output from the log shown in the workflow. And it's completed. And this part of the menu allows one to select a job directory and visualize the results. There is a slider to move through the frames. And here you can see one species deposited and then another. And for these intermediate conditions, there are gaps in the perfect deposition of a layer. Here's the end of the simulation. Again, one can see the defects forming through the system as each species is deposited. So why Chemistream? The value-added proposition is that this framework saves a user's time setting up simulation workflows and saves institutional resources by providing a proven path to HPC cloud computational resources by providing the capabilities listed here. As part of the SBIR Phase 2 funding, we've been working with companies to develop workflows of specific interest. One of these partners is Nonlinear Materials Photonics that has been working with Chemistream to develop quantum chemistry workflows to calculate first and second order response functions for a large number of candidate photonics molecules. This is a quote from Dr. Lewis E. Johnson, CSO of NLM, demonstrating some of the positive feedback we've been getting about the Chemistream framework. More information can be found at the main product page, chemistream.io. This includes project information, including capabilities, including some not mentioned in this webinar, framework documentation, pricing information, and additional tutorials and demos. If you're curious about Chemistream, the main product page includes a link to request a 30-day evaluation license. So that's the end of the presentation section of the webinar. Let's take up to 10-15 minutes for questions from the attendees. After the webinar, you can always email the project lead, Dr. Scott W. Sides, and/or head of marketing, Lance and Nepper, if you have additional questions. Thanks again for attending this Chemistream webinar.
Thank you, Dr. Sides. Let's go ahead and open up questions here. And it looks like we have a few that have come in through our chat. And I'll go ahead and just read them off to you. Let's see here. The first one is, what if I need to spend time tweaking problem setup, but I don't want to pay for cloud computing time?
Thanks, Lanson, and I want to thank everyone for attending the webinar. So one can, if you don't have cloud time, there is a mode in which you can run Chemistream on your local machine. It's really a way of tweaking problem setup and evaluating the workflows and the codes that are installed without using cloud resources. And that's available in the evaluation license version of the code. Thanks.
All right, excellent. All right, let's see here. Next question. I would like to use the code available in Chemistream, but don't need what you showed. Can I just use the codes?
Sure. And so I think I'll interpret that as being that some of the workflows that we showed in the demos might not be exactly what someone needs, but the codes themselves are certainly available. The simulation engines are available, and a user can use only those. And so there's a way through the Jupyter Lab interface to start up a terminal. And in that way, it would essentially look like being at a supercomputing cluster institute somewhere. So you would have access to command line operations in an environment that have all of the basic simulation engines themselves installed, and you could implement your own workflows there. Thanks.
All right. All right, next question.
I want to run hyperbolizabilities with the Dalton package. Are there similar workflows for Dalton as you've shown for NWChem?
Yeah, so the workflows that we showed in the demos are just a sampling of the ones available. And we definitely have similar setup workflows for Dalton as there are for NWChem. And we are, of course, always working on adding other workflows. And so it's always useful to check back with us and keep checking the website for new demos that we're posting as we develop new workflows.
Excellent. All right, and next question. You only showed certain AWS instant types. Can others be selected?
Absolutely. The instance types that come up in the demo are just a default list that are representative of a useful sample from very lightweight instances to very large instances with multiple cores and GPUs. But you can type in, if the instance type that you want to run on at AWS, you can type that in by hand, and it will dynamically look up the capabilities of that instance, and you can use that in the same way as the ones shown in the demos.
All right, and looks like one of the last questions here is, I use the quantum chemistry and MD codes you listed, but I have my own workflow. Is there a way to migrating our current workflow into Chemistream?
Absolutely. There are two ways to do this. As I mentioned before, you can run from the command line without the GUI workflows if you're more comfortable with that, to just access the cloud-enabled versions of the simulation engines. And through the Jupyter Lab interface, you can drag and drop files from your desktop into the session. So that will effectively migrate those files into the running containers at AWS, and you can customize your workflow in that way. The second way would be that since we're in beta testing, we would be happy to consult with any evaluation users on adapting the current workflows with the GUIs to workflows that would be more applicable to their specific needs.
Looks like that's it for the questions that we have so far. I don't know if you want to wait a few minutes or we can go ahead and conclude. If anybody has any questions, they could always email us as well.
No, I think that's good. I just want to thank everyone for attending again, and to remind everyone that if you missed something, the recording of this webinar will be online and available on the chemistream.io website. Thanks again, everyone, and have a good day.